Recently, our client John met his banker to discuss plans for a clean energy building. What he found was a shared passion for building something more, momentum for change. First Horizon Bank. Let's find a way. Go to firsthorizon.com/John. A lifetime of hard work, children laughing in the kitchen, family photos on a restaurant wall, a legacy that lives on. It all comes from the power of a conversation, like the one Tommy Hall had with First Horizon Bank about taking over his father's Charleston-based restaurant business. Now the table is set for a whole new generation. First Horizon Bank. Let's find a way. Go to firsthorizon.com/Tommy. First Horizon Bank, member FDIC.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again, and thank you for joining us on Space Nuts, where we talk about astronomy and space science, and sometimes we talk about space science and astronomy. You just never know with us. Could be all of that. And good to have your company. Thanks for joining us. And today on the program, we're going to celebrate success on Mars. The Perseverance rover picked up a rock. Woo-hoo-hoo! It's actually very hard to do, but they've succeeded. And the life of Ingenuity, the other thing that's on Mars, has been extended, which is really good news. We're also going to investigate a new method for investigating the atmospheres of other planets. And I was amused by this story because it involved putting calculations on a piece of paper with a pen rather than using a computer. I was rather impressed by that. And a story about brown dwarf stars, plus audience questions. Peter wants to know about a clock on Pluto. Apparently we put one there. No, we didn't. But if we could, he's got a question about what we might learn from that. We've got a mysterious person from Colorado who didn't tell us their name about dips in light. We'll explain that later. And David in Springfield has a dark matter question about spiral galaxies. So plenty to talk about on the show today. And joining me, as always, is the good Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. How's it going over there?
I am well. How are you?
Well, fine, thanks, yeah.
Well, the infection capital of Western New South Wales, I think, is probably a more apt name for our location at the moment. But, we're just plodding along, staying at home, going out once a week to buy food. That's about it.
It's much the same here.
Yeah. We're all going through it at the moment. But, the case numbers just keep rising, and we just keep hoping that we reach that magic 70% double vaccination number sooner rather than later so we can get our lives back. But I think we're a bit over a month away from that at this stage anyway.
Yep.
Okay, let's start, Fred. Let's look at our first subject of the day, and that is the Mars Perseverance rover successfully picking up a rock and putting it in a tube.
Well, it's just a little bit more than that, because it drilled a hole in the rock as well.
Yes.
And, of course, this was the issue last time, that drilling holes in rocks doesn't always produce what you want it to. The last time Perseverance attempted to do that, they just got a whole lot of powder that disappeared. So nothing went into the sample tube. But this time they have taken a core sample from a rock, and it is safely, hermetically sealed in the container, one of the containers. I think there are 40 of them or thereabouts that the spacecraft carries. One's already been used and is empty because the powder.
So that once they have a dud, they can't go back.
No, that's right. I think that's right. You can't just refill that one. No. So the second one is now has its it's got its sample, its core sample, safely in this. It's about the size of an old-fashioned piece of chalk, a little bit thicker than a pencil.
Right.
It's you commented on that it was more difficult than it sounds, and one of the reasons for that is that actually taking samples on another planet involves a fair bit of technology, and apparently the sampling and caching system on Perseverance is the most complex mechanism ever sent into space. That's the interim director of Jet Propulsion Laboratory. It's got more than 3,000 parts. Our Perseverance team is excited and proud to see the system perform so well on Mars and take the first step of returning samples to Earth. There you go.
Now there's the magic words, returning samples to Earth. They're not going to do that for a while.
No, that's right. That needs another mission. So what they do is they put the sample in a container and then they leave it on the surface, presumably with a flag or a beacon of some sort, so so the system knows where it is. I don't think there's any thought of Perseverance going and collecting its samples and then bring them all back to a pile, pile them all up so that they can take them
Perseverance takes the sample and leaves it there and then moves on.
Yeah, I think that's the way it works. I think it leaves it and moves on.
Aren't we making this more and more difficult for ourselves?
Well, I guess, in the true tradition of good engineering, picking them up and bringing them back, that's somebody else's problem.
Yeah, we won't worry about that part. That's too hard.
Just leave it here and somebody else will pick that up.
Yeah, good grief. Okay. And the other thing I read that I found interesting was once we do return these samples to Earth, it'll be the first time we've brought back something from another planet. Is that right? I got the feeling we'd already done that.
Not planets. We've done it for the Moon, of course, with Apollo missions. We've done it for asteroids.
Right. That's what I'm thinking of. Yes, of
Ryugu and Bennu and all these the Hayabusa missions, things of that sort.
Yeah.
So that's happened, but never a planet. That's right. It's never been a planet.
Yeah.
And really, there's only one that you could do it for, and that's Mars. You could do it for Venus if your equipment didn't melt in the process because of the temperature on the surface. But
which has happened.
Yes, that's right. Mars is certainly the easiest.
We certainly discovered that plastic and Venus don't go well together.
No, that's right. There's quite a few things don't survive too well on Venus.
Very true.
Living organisms for a start. But it's great news, and congratulations to the team. I think that's a milestone that's well worth celebrating. It's what is it now? 8 months, I think, since it was February since when Perseverance landed. So 7 or 8 months.
And what of Ingenuity? There's news on that as well.
Well, there is too. That Ingenuity has now completed its 12th flight. Remember, it was only going to have 5, I think, was the total that they expected to do, because they really didn't think the little machine would survive all that well.
And we're talking about the helicopter drone.
So I beg your pardon.
Whatever you want to call it.
The helicopter, the Martian helicopter. But it's had its 12th flight. And so what has happened is that there has been a formal extension of the mission indefinitely. So Ingenuity itself will now keep going for as long as it survives and as long as it's providing useful data. But it's going to do what you would expect a drone like that to do, to scout out the interesting rocks and things of that sort that Perseverance can then go and check out, make sure there's no big obstructions in the way, all the stuff that you can do from an aerial mission.
Yeah.
There's a couple of nice quotes from Josh Ravitch, who's the head of Ingenuity's mechanical engineering team. He says everything's working so well, we're doing better on the surface than we'd expected. But he also points out we've actually been able to hand winds greater than we had expected. I think by Flight 3, we'd actually accomplished all of our engineering goals and got all the information we'd hoped to get. And so there was a mishap on Flight 6 when one of its there's a glitch in one of the surface cameras that it uses for navigation, but it recovered from that, and the following flights have been fine. So so what they're planning is to use it to scout the way for Perseverance to go forward to make a safe path for detecting the rocks that need to be measured. And apparently they did that a week or so ago, 3rd of September.
Yeah. And of course, what we didn't mention was that these samples will ultimately be examined for microbial life or ancient microbial life evidence, which is fantastic. I also read, Fred, that Ingenuity's life on Mars has been extended because they didn't have a choice, because Menulog had put in a bid to take over once the once the Ingenuity missions had finished. So we don't want them involved. But the pizza delivery test went really well. That's what sort of sparked Menulog's interest. Yeah.
There you go. That will be it. Yes.
Most exciting. But yeah, more interesting news coming out of Mars, and they're achieving some incredible firsts.
Yeah, absolutely.
Which and they'll probably continue to do so. Now, Fred, let's move on to our next topic. And I read this article and I started scratching my head because it reminded me of the incredible frustration I had during school when it came to mathematics. But what really tickled my fancy about this, and we were talking about a new method for investigating the atmosphere of other planets, is they worked it out with a pen and a piece of paper.
That's the way to do it. That's the way Neptune was discovered. Neptune, the only planet that was discovered with the point of a pen.
Isn't that amazing?
Calculated where it should be, and somebody had a look, and sure enough, that's where it was. So this is something a little bit like that. And let me just explain what we mean by sort of pen and paper mathematics. It's something called analytical methods. The branches of mathematics now are very different from what they were when I studied maths back in the 1960s. God forbid, it was awful. Computers were just coming in, but we weren't really, using them in the way that they use now for modeling, because computers can, build mathematical models of what's happening with observations, for example, and make really accurate predictions that you can replicate reality in a very accurate way with computer modeling. So very, very powerful in its technology. But the analytical methods, what you do in that is make a formula. And then that's, it becomes very easy. You can almost do it with a calculator rather than needing computer modeling. So it's a different way of doing mathematics, and it's turned up in a news item, which is something that I've always found quite fascinating, and that is the way the light from an object, like a planet going around a star, the way its light changes as the planet goes around the star, if you're looking from a distance. And the classic example of that, and it's not a planet or a star, but the way the moon goes around the Earth, of course, we're all familiar with the phases of the moon. Its shape changes. But if you were observing the moon and you couldn't see any detail, you couldn't see the shape of the moon or any of the, the grey areas on it or any of that stuff, all you could see was the brightness of the moon. You can still learn something because you can plot what's called a phase curve. That is to say, as for just thinking of the moon again, as the moon goes around the Earth, because it's illuminated by the sun from different directions, its illumination changes. And if all you could see was its brightness, you plot the brightness against time and you get this phase curve, and of course it will go up and down because as the most of the moon's disk is illuminated, it's bright. As a thin crescent is illuminated, it's quite faint. But the phase curve has locked in it information about the surface itself, the reflectivity of the surface, and the way that would change as it's illuminated in different ways. So, for example, imagine a powdery surface, which is what the moon's got. If the light that's falling on it is coming in at a low angle, it will behave in a different way from the point of view of how much light it reflects, as if it's being directly illuminated from above. It actually has different characteristics. And you can think of that, if you think about, say, a powdery surface being illuminated from the side, what the powder particles are all going to cast little shadows, which will change the illumination.
I get it.
Whereas, say, if it's illuminated from above, the shadows are all hidden by the particles themselves, and so it's brighter. So that sort of information is locked in it. And what has happened? I mean, the theory of this kind of thing goes back actually to the 18th century. It's quite remarkable, and in fact, a man called Johann Heinrich Lambert, and we still talk about Lambertian illumination in the world of illumination science. I get mixed up with this because I sit on lighting committees for the Australian standards, and they're always talking about Lambertian illumination. Anyway, all that notwithstanding, a Swiss astronomer. He's a theoretical astrophysicist. His name is Kevin Heng, the Centre for Space and Habitability at the University of Bern in Switzerland. He and some of his colleagues have published a paper which has a very nice analytical method. It's just the formula basically that solves something called the radiative transfer equation for isotropic scattering. So there's a bit of complexity for this.
Yes, but that's where my brain went. Nah, stop reading.
yeah. So
it's all too much.
Mine did that too, but anyway, you can look at it in a new mathematical way, and that is what has happened. And so they've kind of tested this. One of the things that has been done, and I think this is Dr. Heng has done this work. Cassini, remember the spacecraft in orbit around Saturn? It didn't just look at Saturn; it also looked at other planets. So it looked back towards the inner part of the solar system to Jupiter, and essentially measured the phase curve of Jupiter. This was quite early in the Cassini mission in the early 2000s. So Jupiter has a phase curve that had never really been analysed in depth, and so the new computation that Dr. Heng has developed, the analytical method, he's analysed the Cassini phase curves and can show that the atmosphere of Jupiter has clouds made up of largish, and these are still less than a millimetre probably, but largish particles which are irregular. They're differently sized. It's really very nice science that you can deduce something about Jupiter from a little telescope on a spacecraft in orbit around Saturn, just by looking at the way the brightness of Jupiter changes. So I was really impressed with that. I think it's a nice piece of science. It's got all kinds of echoes. We've not got many minutes left to talk about this, but let me slide quickly to something that's similar in a way. You may or may not be aware of this, Andrew, but if you look at a rainbow, there are certain features in the rainbow that tell you how uniform the particles, the raindrops are. If you've got, there are things called supernumerary rainbows which appear within the rainbow, and the more of those you've got, the more uniform the droplets are that form the rainbow. And so, just by looking at a rainbow, you can learn something about the droplet size of the water cloud of water droplets that's forming it. And this is a kind of analog. So just by looking at the way Jupiter's brightness varies, you can work out something about the particles that are actually in its atmosphere. I think it's really neat science.
Yeah, indeed. Yeah. I also read that they're using the same method to analyse the exoplanet Kepler 7b. So this can apply to all sorts of situations by the sound of it.
It's really going to come into its own with exoplanets, that's right. Yeah. What will really make use of it is the James Webb Space Telescope when it looks at the phase curves of exoplanets, because you can do that without actually seeing the planet. You can look at the light of a star and see slight variations in that brightness that come from the phase curve of a planet going around it, even though you can't see the planet as a separate object. Kepler will certainly make use of all that. So I beg your pardon, James Webb Space Telescope will make use of all that, I think we'll learn a lot. And this, this technique that has been developed, I think is a really neat piece of work that contributes to that.
Yes, as long as they don't forget when they launch the James Webb Telescope to send a pen and a piece of paper up with it.
That's the trick. You've got
Otherwise, it could be in trouble.
Oh,
could
yes,
be in
absolutely.
trouble. Yes. No, fascinating. And if you want to read that article, I think you'll find it in one of the papers, Nature Astronomy.
Nature Astronomy, yeah. That's where the paper is, which I haven't looked at because I'm too scared to open that. It will just be mathematical gobbledygook of the kind that used to send shivers down my spine.
Yes. As soon as I saw mathematics mentioned in the article, my brain froze. But there'd be people who'd be champing at the bit to read it.
Yeah.
So Nature Astronomy is where you'll find the paper.
Yep.
This is Space Nuts with Andrew Dunkley and Professor Fred Watson. Let's take a short break from the show to talk about our sponsor, NordVPN. Now, VPN is a virtual private network, and it basically enables you to protect yourself from hackers or from anybody who wants to impinge on your privacy. NordVPN is the fastest in the business. It's the most popular VPN on the market, and it is very inexpensive. It's the one I use, and it is available on multiple devices. It's got some features that I think you'll really enjoy. You can have it running simultaneously on up to 6 devices, including your smart TV, and you can take it with you. It's mobile, so it's not something you can only use on a computer that's plugged into a port in your wall. You can have it on your mobile phone, on your tablet, anything you like that has access to the internet, so that you remain secure, especially if you're using public Wi-Fi. That is a haven for hackers, and they can get all sorts of information from you without you even knowing it until it's too late. It's very secure in terms of its internet connectability. They have a strict no logs policy. They don't track, they don't collect or share any of your private data. It's none of their business, and they don't want to know. So that is a very attractive thing. And it's very easy to use. It's a one-button click. That's all. Download it and click. And that's all there is to NordVPN. And that's what you want. You want simplicity. You don't want to sit there logging in every time, trying to remember passwords and faffing around with all that sort of rigmarole. And it's fast. As I mentioned, it is the fastest VPN on the market. You don't need to sacrifice speed for better security. And in some cases, it's actually faster than your standard internet connection. I don't quite know how that works, but it does because I've witnessed it. And you can access your content and enjoy a full range of streaming with your subscription. And they have servers everywhere, all over the world, over 5,200 servers in 60 countries. No limits, no borders, no internet censorship. And if you're a sports fan, this is something that will interest you. You can log on to a server in a country that's showing a sport that you want to see that would normally be geo-blocked and watch it on whatever network. It's really simple, it's really inexpensive, and it really is the best VPN out there. Now, if you'd like to take advantage of this, we have a special offer for our Space Nuts family. All you have to do is go to the URL that's been created for you, nordvpn.com/spacenuts. Take advantage of the special offer. It is really quite impressive. In fact, I'm going to show you what it does. So nordvpn.com/spacenuts. You put that URL in and it brings up a special deal, a 2-year plan plus 4 months for free. That's 2 years if you sign up as a Space Nuts listener, and 4 months for free, and they'll even throw in a 30-day money-back guarantee if you're not happy. So if you'd like to grab that deal, you can do that right now, nordvpn.com/spacenuts. Now back to the show.
3, 2, 1.
Space Nuts.
Thanks for joining us. And we often talk about the Space Nuts shop, which is on our website, spacenutspodcast.com or spacenuts.io, whatever you like. And look what turned up. If you're a YouTube viewer of Space Nuts, you get a big advantage right at this moment because I can show you these. The new Space Nuts stickers. and the logo designed by my brother Steve, who came up with that great slogan of ours: "Science, Space, and Stuff." So there they are. But you can find them on our website. We've got a link to the Space Nuts shop there if you're interested. Now, Fred, let's move on to this next topic, and it is all about brown dwarf stars. Now, we know of about a couple of thousand of them in our galaxy, but they think there might be more and more because they've found one that's different, and that could open the way to there being more and more and more of these things that we didn't know about. And from what I understand, this one was quite an accidental discovery, which
Indeed.
also correlates to the name of it.
That's right. Yes, I love the name. Its proper name is WISE-A J153429.75 minus 104303.3. That's
Say
its
that
name.
10 times fast.
But they nicknamed it the Accident, and I like that very much. We haven't really talked much about brown dwarfs on Space Nuts, which
Not
is
much.
a pity. One of my former colleagues, Chris Tinney, who's now at the University of New South Wales, was one of the pioneering pioneers of brown dwarf studies. Really interesting objects, and in a sense, they sit between gas giant planets like Jupiter and stars like the Sun in their mass range. So they're sometimes called failed stars because, although we do define them as brown dwarf stars, but it's because they don't have the nuclear fusion that generates all the energy at the center of a star like the Sun. That nuclear fusion kicks off because the temperature of the cloud of gas that is about to form the Sun is increased to 10 or 15 million degrees by the compression of the gas. So you need a lot of gravity to produce that compression, and that switches on the nuclear fusion, and then you've got a star. If you have a cloud of gas that collapses but doesn't have enough mass to raise the pressure and hence the temperature to that critical, 10 or 15 million degrees or whatever it is, then you get something which is smaller and has some features of a star, but isn't a star. And that's what's called a brown dwarf.
Right.
And the features that they have is that they do emit energy at a very low level. And in fact, they're called brown because they radiate most of their energy in the infrared region of the spectrum, the redder than red light.
Yep.
So they were, even though they were hypothesized actually a long time ago, they were only really discovered when infrared astronomy came of age in the 1970s. So now, as you mentioned, we know of a couple of thousand of them. So they're sort of intermediate between planets and stars. They probably have weather, a bit like planets do, but they do radiate energy a bit like stars do. And it's not the fusion of hydrogen which is causing that radiation. It's something called deuterium burning. It's a low-level nuclear process that is enough to keep the star warm, but not to make it hot. So when you're looking for brown dwarfs, what you do is you look for stars that are sort of faint in some wave bands. For example, a brown dwarf, the light of a brown dwarf star contains virtually no blue light. So if you're looking for an object that's radiating the blue, you're not going to find a brown dwarf. But once you move your wave band up to the infrared, they get brighter, and it's because they're cool. So cold objects, you know this from just thinking about red hot metals and white hot metals. When a metal's white hot, it's very hot. But as it cools, it goes redder, and it just goes redder and redder, and eventually you can only see it in the infrared spectrum. The same is true with stars. So infrared stars that are cool, you detect by their infrared radiation.
Otherwise known as Fonzie stars.
That's a very accurate description, yes.
Okay.
which confuses things now. But never mind, we'll move on, because the thing about the accident and the star that's called the accident is that it's got the right sort of brightness in the wave bands that suggest that it's very cold. In other words, in the infrared there, so it's kind of, well, it's faint in the visible spectrum, put it that way. So there's just nothing there. But when you look at certain of the other wave bands, and what we're now doing is dividing infrared up into slices. And in fact, we do that. We call it near infrared, mid-infrared, far infrared. These are all well-known technical terms in the trade. Some of those wave bands, it's actually brighter than you'd expect it to be. And that's a puzzle. So it's giving you a mixed message. It's saying, in one wave band, it's saying, oh yeah, I'm cold, I'm a genuine regular brown dwarf. But in other wave bands, it's saying, no, I'm actually quite hot and bright. There's something interesting here. And so the people who do the physics of this sort of thing have thought about it long and hard, and have kind of worked out why this should be. The bottom line is that this star, the accident, is an extremely old star. So it was formed when the gases from which stars are formed was not as rich in heavier elements as it is in more recent times. You and I have spoken before about how the amount of iron in a star spectrum is an indicator of its age. Stars with virtually no iron are very, very old, because they were formed from gas that was really just hydrogen and helium. There wasn't anything else. But as time goes on and stars themselves generate the iron and then come to an end, spread that among in the interstellar medium, so that new stars form with much more iron. That's what we call the enrichment of the interstellar medium. It's how these elements appear. So the thinking now is that the accident actually formed at a time when, first of all, there was less carbon than there is now, or than there was more recently, because the carbon is one of the sort of indicators that suggest it's brighter in this region of the spectrum than it should be. If it had more carbon, it would be fainter in that region. And so what they're saying is, yes, this is a star that formed from the primordial mix, not quite primordial. It would have had some heavier elements in it, so it wouldn't be part of the first generation of stars, but dates back to the early years of the universe, perhaps 13 or so billion years ago. So it's a very, very old star. And they now suggest that there might be a whole population of these things that have been missed because they've got this peculiar response in their different wave bands.
Yeah, fascinating. It's also moving rather fast.
Yes, it is. That's correct. It's whizzing round. Let me do the calculation in my head. It's several hundred kilometres per second, about 800,000 kilometres per hour. Yeah, so you divide it by 3,600, which I'm doing in my head, and getting about 200 kilometres per second, I think, is the answer.
Wow.
Roughly, very roughly.
That's moving along. It's not far away either, 50 light years.
Yeah, it's quite close, that's right. So whizzing by. So yes, a really interesting object that might open the way to studies of a whole new population of these weird brown dwarfs, accidental brown dwarfs.
Yes, indeed. And I just received a note from the Department of Political Correctness. We're not allowed to call them brown dwarfs anymore. We have to call them stars with disabilities. So,
yeah,
sorry about that.
Confusing two different sorts of dwarfs, I think. Yeah.
Maybe.
Yes.
Just insulted dwarfs.
No,
sorry about that.
No, I don't think we have. No.
Okay. You're listening to Space Nuts with Andrew Dunkley and astronomer at large Fred Watson.
Recently, our client John met his banker to discuss plans for a clean energy building. What he found was a shared passion for building something more, momentum for change. First Horizon Bank. Let's find a way. Go to firsthorizon.com/John.
Space Nuts.
Okay, this is the part of the program where we hand control over to the people that know more than we do, the audience. And we start off with an audio question. This one comes from Peter in South Australia.
Hello, Professor Watson and Mr. Dunkley. It's Peter Hennis here from South Australia. Have you heard of a thought experiment? Let's say we go to Pluto and place a clock on there, one that's super large that we can see with our naked eye from Earth. Now, let's say we know that Pluto, the light from Pluto takes 5.5 hours to reach us. So if Andrew's outside of the telescope with his eyes looking at Pluto, would he see the same time on that clock that Professor Watson would see if he was in a big, powerful telescope looking at the same clock? Would there be a difference in the time that both of them can see at that time? Thank you. Love the show. Bye.
Thank you, Peter. Lovely to hear from you. Hope all is well in South Australia. I was supposed to be there next week, but not going to happen. But next year, definitely, we've rescheduled. I think what Peter's getting at is, would the magnification of a telescope change the perception of time as viewed from a clock on the surface of Pluto? And to my way of thinking, that would be a definite no, because I think you're both looking at the same thing from the same place at the same time. Therefore, the time on the clock would be the same.
Yeah, that's right, Andrew. So the way to think about this is to think about what's actually happening when light travels from an object like Pluto. It's photons of light, which are coming at the speed of light, 300,000 kilometers per second, taking their 5-ish hours journey or whatever it is. So the stream of photons that leaves Pluto arrives on Earth. And what we do, you with the naked eye and me with the telescope, we both basically sample that same stream of photons. So there's no fundamental difference between them. It's like rain falling, if you think of it that way. You're both going to get wet.
Yeah.
It is the stream of photons. One of those part of that photon stream is intercepted by your eyes, and part of it's intercepted by my telescope. But they see the same photons. They see back to the same time on Pluto, which is So they both have the same clock.
All right.
Or showing
let me augment the question then.
Or do augment it.
I'm on Earth looking at the clock, and you're on Mars. What happens then?
So yes, so then there's a different time involved because the travel time is different. So if Mars was in a place in its orbit where it was nearer to Pluto than the Earth is, which certainly happens when it's near opposition, then Pluto, so me on Mars would see the time on Pluto earlier than what you would see. I beg your pardon, I would see, wait a minute, let's get this right. I'm going to see...
Well, if Mars is closer to Pluto,
we'd see the same time, but you'd see it later.
Right.
That's right. So, the time delay looks more for you than it does for me. So you'd see the time earlier. But the problem is, I'm glad you asked that because it actually goes to the real physics behind this question, which is the notion of simultaneity, and that is. In the universe, nothing's simultaneous because the information about it always has to take the travel time. And that's the difference between Einstein's universe and Newton's. In Newton's, everything happens at the same time. Simultaneous means two things happen at the same time. In Einstein's, it might mean two things seem to happen at the same time if the light travel or the light travel time is the same, which it would be if we were both on Earth. But the notion of us receiving the signal at the same time depends on how far apart we are and how we are moving relative to one another. That's another aspect.
Yes, I get it. Because I had to learn that for my time travel stories when I write my
Yes,
book.
of course.
You've got to
all this.
understand all this. But you can, without looking at the sun, something as close to us as the sun is a good example of it, because what we look at happened 8.5 minutes ago.
It did, yeah. That's right.
So we're not actually seeing anything happen in real time because of the distances.
And in fact, that's such a fundamental part of astronomy that you ignore real time. You just talk about, the time as we perceive it from Earth, because it's the only way we've got of getting information.
All right. Thank you, Peter. Lovely to hear from you, and I hope that covered your question. We'll go to Colorado now, and this is a random listener. That's actually their name, random listener, so we'll call them that. No, I think it was a case of the name either was omitted or something went wrong, but I hope you know who you are. When astronomers use light or the dip in light from stars to tell what the stars are made up of, do they account for the heliopause of those stars? Would the interaction between the star's radiation and the radiation in interstellar space create a reaction that would affect the light spectrum of the star?
Yeah, in principle it does, but it's such a small effect that it's pretty well ignored. So when the dips in light that the random listener is talking about are what we see in the spectrum of the light when we break the light up into a rainbow of colours, and we get these dark lines, which if you plot them on a chart, they look like dips. So the dark lines, we call them absorption lines, they tell us what the elements are that are in the star's atmosphere. They tell us a number of other things, though. They do tell us about magnetic fields. And in a star, often like the sun, the magnetic fields are very strong, and actually they do affect the dips. In fact, they split them into multiple components if the magnetic fields are strong enough. So then you've got light traveling through another magnetic field out from the star's surface past its heliopause. That's the region where its magnetic field ceases to be the major influence. And you're now talking about magnetic fields that are infinitely weaker than what you have within the star itself. So there's actually no need to compensate for them. But it's a question based on some good physics. It's on the right track. So thank you very much for the question.
Thanks, Random. Lovely to get your note, whoever you were. Now, David in Springfield has a dark matter quandary for us. Evidence for dark matter was found by observing that stars of galaxies all move at the same speed regardless of whether they are near or far from the galactic centre. How then does a spiral galaxy even form with all stars moving at the same rate? Like water spiralling down a drain, the spiral shape requires the stuff towards the outer edge to be moving more slowly than the stuff nearer the centre, right? Dark matter should make formation of spiral galaxies impossible. Why aren't all galaxies of the non-spiral globular type if dark matter is real? Now, I think we have touched on this before, and I think I recall you saying that spiral galaxies are actually a myth or a trick of the eye.
They're an illusion, yeah, in the sense that it's what traces out the spiral arms is the bright young stars that are formed by. I got picked up by the copy editor of my new kids' book for talking about bright young stars because it sounds like the people you see on TV.
Yeah,
so
that's the first thing I thought of.
Yeah, bright newly formed stars. That's right.
Right.
So bright newly formed stars. So that's what traces out the spiral arms. And it's caused by this, what we call a density wave passing through the disk. But I want to go back to David's question because there is actually a logical flaw in what he said. Forgive me for sounding critical. I do not mean to be, but it doesn't work that way. So the point David makes is exactly right, that no matter where you are from the stars, from the center of a galaxy, the stars are all moving at the same velocity, roughly, very roughly, a couple of hundred kilometers per second. However, if you had a string of bright stars in a galaxy going from the center to the edge, and they're all rotating in this fashion, you would still get a spiral, because the stars, even though they're moving at the same speed, the stars at the outer edge have got much further to go around the galaxy than the stars near the middle. So it will still form that spiral pattern. When it won't form a spiral pattern is if the galaxy rotates as a solid body. In other words, the speed of rotation is proportional to the distance from the center. That's what's called solid body rotation. If you imagined a solid disk of material, that's how it rotates. The speed is actually physically, in terms of its linear speed, it's slower near the middle than it is at the outer edge. Yeah. The outer edge has to rotate faster, so it remains intact. So solid body rotation would not produce spiral structure, but constant velocity rotation does.
Okay. Solid body rotation would be like a vinyl record.
Yeah, exactly. Perfect analog. And you've touched on something that is uppermost on my mind, because this room that I'm in at the moment is my new study, and I'm trying to find a place for my vinyl records.
Excellent. Yeah, I can see shelves behind you. That looks like a good spot.
Up. Yeah, it's all good there.
Yeah, fantastic.
CD racks and everything there.
Oh, wow. You're getting there.
I'm getting there.
Better than cardboard boxes.
Well, they're still here as well. There's a pile of them down there.
Oh, dear, oh, dear. Okay, so I think we've squared David away.
Yes. No.
We've told him how very wrong he is. And
No, I didn't.
No, we didn't. Like that. No. But, that's why people ask questions, so that they can get the answers they deserve and need to know. Nice to hear from you, David. Thanks for the question. Thanks to everybody who wrote in or sent us audio questions. You can do the same on our website. There are a couple of options on the website for putting your questions in. There's, if I go back to the homepage, you can click on the AMA tab up the top and send us an audio question that way, or a text question, an email type question. Or you can click on the tab on the right-hand side, which is a different audio avenue called SpeakPipe. So that's another way of sending us questions. Whatever you choose, as long as you've got a device with a microphone, you can send us an audio question. We love to hear your voices, and we don't mind if you tell us who you are or where you're from. In fact, we'd love to know that too. So and to be honest, we are a few shorter questions. They've dried up at the moment. So if you've got something in mind, please send it to us, because normally when we hit a round figure episode, we do an all audience episode in terms of questions. Next week's 270. So, if we can get enough questions, we'll fill her up. Otherwise, we'll find some topics. We'll just play it by ear at this stage. But love to hear from you. And while you're there, check out the Space Nuts shop, because you might be able to get some of these. Space Nuts stickers and all sorts of other bits and bobs there. Fred, that brings us to the end of yet another episode. Thank you so much. Been great to talk to you.
I've enjoyed it very much, Andrew. It's been a good chat, and we'll chat again soon with episode 270. Wow.
Yeah.
How did we get to that?
We did it 269 times before.
yes, that's it.
I think. All right, Fred, good to catch up, and we'll talk to you soon.
Sounds great. Thanks, Andrew.
Fred Watson, astronomer at large here on Space Nuts. Thanks to Hugh back in the studio, who pulls all the strings and dings all the bells and makes all the whistles blow and whatever else he does to put it all together. And from me, Andrew Dunkley, thanks for your company. We look forward to your presence on our very next episode. Until then, it's bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.